Hopefully everyone can hear me. I think everything's going well here. So we're going to be talking today about reducing temperatures. Oh, thank you. And eliminating the PVC oven. So I'm going to start out from the adhesives and sealants side, and then we'll hand it over to Craig to talk a little bit about the decorative stack. So looking at the automotive paint shop, this is sort of where we're going to think about energy intensity of the wet-on-wet processes. This is just a general depiction of the traditional, or rather conventional, automotive paint shop process. So if you follow along this infinity, we're going to start here at the top left. Here we start with our pre-treated body in white. That's going to undergo the e-coating process. From here you'll get a rinse, followed by the e-coat bake. From there we cool, sand, and then apply the sealer. And this is going to be my main focus here. This is robotically applied. And in the conventional process, there's a dedicated sealer oven right here in the center circled. That is traditionally at 140 degrees Celsius. That's a dedicated oven for the sealant. From there, the two base coat layers are applied, followed by the clear coat. Then there's a final bake in the clear coat oven depicted here. And that's sort of the general depiction of the auto paint shop process. Something I'd just like to emphasize, if we look at this pie chart, is that the ovens and paint booths are about a 70% contributor to the total energy intensity of this process. You can see the others, so pre-treatment, plant heating, and other energy expenditure are fairly minor contributors. So that's where we want to focus our efforts on some of these low temperature cure technologies. Moving forward, I'd like to just discuss the wet-on-wet process and sort of its evolution in time. So traditionally, when we're thinking about a compact process, this differs from the conventional process in the sense that we've eliminated a primer oven. But when we talk about a wet-on-wet process, what we're really talking about is sequential layers applied one on top of the other, wet-on-wet, that will then all co-cure in the same oven. So here, we can think about a traditional process, 3-wet or 4-wet, where we have our B1, B2, and then clear coat, all co-curing in the clear coat oven here at 140 degrees Celsius. If we envision a high temperature 4-wet process, we could envision eliminating the PVC oven here and then having the PVC sealer co-cure with those other 3 layers, and that would make that a 4-wet process. So if we move down, we can see we can go to 110 C in the clear coat oven. We can also reduce that to 80, and so that helps with some of that energy intensity in terms of lowering oven temperatures. You get lowered CO2 emissions. However, we can also envision a 4-wet compact process wherein we eliminate the PVC oven. However, that would mean that the sealer would need to co-cure along with the decorative layers in the clear coat oven. And now that that's down at between 70 to 90 degrees C, that demands a sealant that can actually cure at that 80 degrees C temperature. So we would need to eliminate that dedicated PVC oven. And that's sort of where we come in from the R&D division. And I think this is sort of a point that Ed was alluding to earlier, is that you can only go so far, I guess, within the certain formulation bounds of your given technology. And so, like he was alluding to, this kind of a process would demand a brand new technology. So I want to get just into the value prop a little bit in terms of what's in it for the OEMs that might be interested in this technology. So looking at low temperature cure 4-wet, this enables a number of degrees of energy savings. If we think about moving from the conventional process to the compact process, I alluded to the fact that we're eliminating there a primer oven. That actually takes down our energy intensity pretty significantly. As you can see here in the following waterfall chart, it takes us down about 100 kilowatt hours of energy expenditure per vehicle. Moving that to a high temperature 4-wet, we're eliminating the PVC oven. And then, as you can see, taking down the clear coat oven further, we get additional reductions. And overall, a low temperature cure 4-wet process at 80 degrees C can save approximately 200 kilowatt hours of energy per vehicle. And one key aspect to that is that we can now bring plastic parts in line. So traditionally, the plastic is painted separately and then appended to the auto body. but when we're at that 80 degrees C cure temperature, the plastic is actually amenable to the body paint shop process. So we no longer have to paint that separately and append it on, due to the reduced risk of warping or other, deleterious impacts. That also helps with things like color matching, in addition to the energy you're saving by, eliminating that additional process. This just sort of shows that from a cost perspective. So before we were looking at energy. Now, as we can see here from this waterfall chart, you look at body energy savings, CO2 savings, and bumper energy savings. That's offset ever so slightly by the increase in formulation cost of a newer sealant. However, we can assume that if we're looking at about 150,000 builds on a given line per year, this could translate to approximately $1.2 million of potential annual savings. So this is one of the key value props of this process. I'd like to just show a summary now of some of our technologies that we're deploying. So you can see over there on the right, I won't read it off to you, but you can kind of see some of those key points. But in general, we've developed a 1K multi-purpose sealer. We can achieve full cure now down to 80 degrees Celsius metal temperature with lap shear strengths between 1 to 2 megapascals and tensile elongations between 150 to 250%. We can recommend this for both greenfield plants, so brand new lines utilizing low temperature cure paint shops, but it also supports brownfield plants in the sense that we can eliminate ovens and reduce oven temperatures and still be compatible. Now to get to some of the technical aspects, if we think about sealer technology in terms of a traditional PVC plastisol, these don't have what would be considered as a traditional stoichiometric chemical cure. These are 1K systems. They are dispersions of PVC particles in a liquid plasticizer. And now you can see the loss modulus change in the diagram at right as we increase temperature. So as we ramp the temperature of a PVC plastisol, we initiate gelation. That's when the red plasticizer here is absorbed into the PVC particles. That causes the particles to swell and then eventually interact with one another. And when those polymer chains eventually entangle, that's how we get to cure in a PVC plastisol system, or fusion, which is perhaps the more precise term here. And that's when the swollen particles are purely entangled, and then from there we get essentially a solid film. Just to emphasize this concept, like I said, we don't want to think of this in terms of necessarily a stoichiometric chemical cure. Rather, we can envision it as a bake window where we have this two-dimensional space of temperature over time where we get optimal curing. And this is essentially anywhere where our temperature and time parameters allow us to get a film that's of sufficient quality to address an intended application. So as long as we're in here, we're generally fine. Extending the time of cure or the temperature can continue to increase performance properties like strength and elongation. However, if we're in this underbaking regime, we can get a lack of mechanical properties. And additionally, with overbaking, so at extended time and very high temperatures, in a PVC system, we undergo this autocatalytic degradation brought about by the evolution of hydrogen chloride. That can lead to yellowing and loss of mechanical properties where you'll actually begin to start embrittling the material. So we want to be in this general window, and this can be shifted depending on the formulation space you're working in. So just to look at our new technology that we're offering, these are some of the key performance parameters. We do have a formulation space in which we can work to address certain customer-specific requirements. With storage stability, we're looking at 35 degrees Celsius over 72 hours. We want to see less than a 30% increase, so generally we can achieve that. And that can go even further, just depending on different formulation additives and the space you're working in. It all depends on the final cured properties you want. We can also reach quite low viscosities and a different range of densities depending on our additive packages. I also want to just point out that this technology is amenable to a broad bake window. So you can see, as I alluded to earlier, we have a bake window at 80 degrees C, which would be sort of our minimum here. We can get about a megapascal of tensile strength with about 200% elongation. But as we increase that, so if we were to envision placing this on a conventional line all the way at 140, where you might see a traditional sealant, we can increase that further. So we get about a doubling of tensile strength with a tensile elongation of about 250%. So amenable to a broad bake window can be used with conventional processes or the low temperature cure for wet proposal. And finally, I'd just like to show some lap shear performance. So this gets at both the strength of the material and also the compatibility and adhesion to electrocoat. So as you can see over on the left, these are just some representative images. This is actually on PPG Epic 300 E-Coat. But both at 80 degrees C and 140 degrees C bake, we get pure cohesive failure, which is what we want to see. That shows that you have generally greater adhesion versus your cohesive strength of your coating. And here, the lap shear strength, so that concept of the broad bake window is kind of brought out in some of these data. So we can see that at 80, we get around a megapascal to 1.5 megapascals of lap shear strength. And this increases to around 2.5 then at the 140 degrees C overbake. And additionally, I'd just like to point out that we're compatible with 2 competitor E-coats as well in the low bake space. So that's satisfying to see. I think with that, I've really covered the A&S portion of the talk, and I'll hand things off to Craig.
All right. Thank you, Dorian. So Dorian did a very nice job up front explaining kind of what some of the compact options that we've looked at PPG, and some as like our B1, B2 process, the traditional 3-wet or 4-wet. It's been commercial in the 3-wet form for almost 15 years now. So when we started to look at what we wanted to do to develop our decorative low temperature cure options, we were going to base it off of that because that's already giving us a great ability to reduce footprint, reduce energy already, and we can bolt on additional savings and productivity using that. So, depicted here, basically I'm hoping what everyone sees between the left-hand side where we are today and where we're looking for low temperature cure, there's really not much difference, and that's, like I said, very intentional. There are some features that are really important that we want to make sure that we maintain. The system we're looking at, the current system is a 1K, 2K. If you look at the B1, B2, and clear coat, we want to maintain that in the new system and not maybe go to say a 2K B1 layer, which can cause some issues. Or if you're not doing that now, you don't have that equipment, you have to buy 2K equipment. We're trying to avoid capital costs there, obviously. And then even maintaining a 2K system, that can be some issues, more maintenance down the road, and also cause some issues with dirt, obviously, because that material can cure on its own. So we really wanted to make sure we could maintain those positive attributes into our new system. And really, like I said, really the changes, we're now going to be dropping that final oven set point to say between 90 and 110. So that's what we see on the exterior of the vehicle, and obviously we'll see maybe something 10 or 15 degrees lower that on the interior sections. So going into the system, they have this broad bake range we're looking for, between essentially 80 and 110 with that 1K, 2K format. There were some challenges that we knew up front that we're going to be facing, trying to drop that bake temperature, still maintain really what we're looking for, what current systems at 140 can do. One thing that came up, something we call standalone performance. Some customers do not spray clear coat on their interiors, so in door jambs, under the hood. They actually just spray the base coat only. So, at a 140 bake and the chemistry is there, maybe not difficult to maintain those basic chemical and scratch properties. But if you drop that temperature down, it's a bigger challenge to be able to get that performance and yet still have that layer perform well in the full stack. If we go to the ultimate lower in temperature there, adhesion on multiple substrates. Prior we would just be worried about adhesion basically to E-coat. But in the new systems, plastics definitely are coming into play if we're going to want to actually harmonize and do plastics online. So a lot of different substrates out there, and being able to stick well to E-coat and also these different plastics really were some challenges for us especially on our B1 layer. Humidity resistance, and again, some of these kind of properties along those lines, I bring those up because something we learned very early on. Heat is a great equalizer. In current formulation practices, you may have some materials in there you use that maybe are not great for cure, but again, when you're baking at 140, it can really cover up a lot of ills, let's just say. When you're working at low temperature, you really have to be very exact about what you're using in the systems, and things have to be either neutral or positive for that cross-linking mechanism. Negatives are not really an option at that point. So again, a lot of work to do, simplifying formulations. We had some talks earlier on things that keep getting added. We kind of had to take a step back and make sure we understood what everything did there and its effect on the cure. If you look at the clear coat, again, that's the top layer that protects the entire stack, right? So the 140 bake clear coat has a lot of work to do, scratch resistance, chemical resistance, things along those lines. The lower bake ones have to do the same thing. There's really no ability to step back in any of those properties. Other common there too, we talk about selective migration of the crosslinker from the clear coat. Again, that's an important factor, and again, in the low temp systems on the full stack area to be able to, augment and provide robustness there on overall properties. So again, working on that basically outside of maybe traditionally materials we were using and looking at more different materials to be able to be more robust in that space. So what did we actually decide to develop? And again, low temperature cure, there's been discussion about this for some years, and PPG had to have kind of a come together moment on like, what were we actually going to develop from what the market is asking for us? And we actually came to two different approaches to kind of cover some of these trends that we've covered so far earlier today on what can actually do that. So the one we call migrational cure, is one where customers do have to spray clear coat on all surfaces. That would include the interior. The nice thing about that is we can actually get down to cure temperatures as low as 80 degrees with that system, which means it really opens up the opportunity for using plastics, multiple plastics, even the more difficult ones like polypropylene or ABS. So really, like I said, the only negative there is right now, if you don't have, interior clear coat spray capability, you would have to add that. The second one, I alluded a little bit earlier to the standalone approach and basically having that base coat be able to perform as your top coat. That one there, again, obviously we don't need clear coat on the interiors, but again, with that technology, we do have to have a little bit of a higher bake temperature. So we say the interior, we'd like to have that 90 degrees or above, which means you're going to set your exterior probably about 10 or 15 degrees above that. So just going into a little bit more in the actual what we did in the development here. So on the migrational cure side, as I mentioned, making sure that we have effective migration of hardener from the clear coat. It took a tremendous amount of effort to make sure we were getting the right materials that could provide that migration, but also you still have to have that clear coat that performs at the very high level, with the crosslinker left there available. So a lot of work to be able to do that, to be able to maintain that again robustly over the different film builds for the layers below. When we look at actually the B1 and B2 layers, again, the big point there is the adhesion to multiple substrates. So again, we really had to work with the resin systems, especially in that B1 layer, to make sure that we had good adhesion to traditional E-coats, but then also had the capability to have equally strong adhesion to the different plastics there too. And again, the B2, the color layer, again, making sure, again, having good intercoat adhesion, and again, back to the humidity resistance. Again, we can't take any steps back from where we were looking, from the current 140 bake type systems. And just quickly depicted there, some of the work, again, talking about the multi-substrate, compatibility. Again, we have E-coat and, multiple plastics there that we've done our normal crosshatch and a Karcher or a water jet type testing on to get good robustness from those layers. In the standalone cure side, we actually did a little bit more novel resin work on this side to be able to enable that base coat to perform as that ultimate top coat layer there too. That was a challenge, be able to drop the cure temperature about 20 degrees, but maybe what a traditional chemistry could do through resin design. And again, we were able to accomplish that. Again, the depiction I kind of have down here below, some of the, we like to have our molecule photos in here too, of the different components, in a pigmented system, your resin, your crosslinker, your pigments, and your additives. Again, just really trying to say again, we have to be very deliberate on what we choose there to make sure all those components are contributing in a positive way. One other challenge with this system that we had designing it, what kind of specs do those interior standalone areas need to have? We did a lot of canvassing with our different through voice of customer earlier on, and it was very difficult to maybe get a nice standard set of specifications on what those interior ones actually had to do. I think there was a lot of discussion on at 140, things are generally pretty good there for everything, so there wasn't a lot of specific specs there for that. So we had to come up with some of our own to do some screening. And again, sometimes they were very simple. This had to do some solvent rubs, some pencil hardness, and some of those things online. Really was allowing us to, really kind of, down select technologies that didn't work and ones that did actually well for that type of performance. So I'm usually the kind of guy who brings panels to show to a presentation, but obviously this venue can't do that. So I just want to show a couple of pictures, kind of bringing everything back full circle on the full system that we're showing here with the ANS layers plus the decorative layers. The photo on the left is actually, photos on the left are actually more of a solvent-borne system at a higher bake, so showing again we're getting good compatibility even at a higher bake with these new sealers. But on the right actually is the migrational system we've been talking about here on the previous slides, and again showing good compatibility, no cracking, no de-wetting or anything along those lines with the B1 B2 system. Okay, I think this is actually our last slide, just to kind of summarize where we are combining this full process with the ANS layers with decorative for the low temperature, higher efficiency paint shop. Again, the things we're looking to do in terms of carbon footprint, avoiding capital by having to require new equipment with our systems, being able to be more efficient if we want to bring plastics online. Really something we really focused on with this technology that we've developed. And again, we've been working on this, and we actually are currently in the process with the decorative layers, the migrational and standalone with trials or pre-trial activities with some customers globally, and on the 4-wet side, the core seal, low temperature sealer, we're in the scale-up phase for that material. I'd like to thank everybody. Appreciate just giving us the time to talk to you today about this exciting new technology, and happy to take any questions.
We do have a couple questions from the app. The first one is, what are the disadvantages of having uncured sealer through the process until the top coat oven, and how can they be addressed?
Yeah, so I guess generally I would say one of the greatest challenges is compatibility. So we showed some of those images. You have to be sure, and this is all, just part of the formulation space, but you have to be sure that you have compatibility, because it's possible, certain additives or something will, interfere with that top decorative layer. And so it's something you have to be aware of, and it's why it's good to, check these things along the path, as you're iterating on your formulations. But I would say from a technical perspective, it's just ensuring that compatibility.
And I'll throw out there too, one from the decorative side that we had heard about was potentially an issue was, before the body enters the actual paint shop, it goes through that feather dusting process, right? So while we have to make sure where the sealer is, none of it is actually exposed, or you could actually create a real mess, practical aspect, but yeah, it's definitely something that came up as a potential issue that needs to be aware of, so.
Okay, next question. Would the wet sealer be compatible with waterborne and solvent-borne top coat?
Yes.
Yeah, so I think, you could actually just, go back one slide. I think you addressed that pretty nicely, Craig. Yeah.
Next question. Do you have any appearance data on these systems?
Yes, again, the target of all the work we did, especially on the top coat side, was to match what the current 140 B1, B2 with the 2K clear coat system can deliver. That's appearance, that's color, and that's, back-end properties. So we designed it not to take any step back. So if somebody's interested in talking further, we can share some of that data, but the target was be equal to where the current system is.
Okay. Any questions from the audience? Additional questions? No? Okay. Thank you very much.
Thank you.
I enjoyed it.
Thank you.